E3 mainly talks about the nuclear physics. We are going to discuss the basics of nuclear physics. So we will start with the structure of nucleus. Okay. In structure of nucleus, we first know that the nucleons, when we talk about it, is basically protons and neutrons. And its structure, the nucleus is formed with protons and neutrons. If we have known the symbol, there's A and Z. A represents mass number, that is number of nucleons, and at Z represents atomic number. This is something that we know. We can also talk about the neutron number, that is A minus Z. Okay, and then there are examples of how we can write this in. For a proton, it is 1 1. For neutron, it is 1 0. For electron, it is 0 minus 1. Positron 0 plus 1, and photon is 0 0. So we can write all those things for the individual elements also, and for the particles as well. Now, if the particles have same number of protons but different number of neutrons, those are called isotopes. Now, isotopes do have similar chemical properties but have different physical properties. Chemical properties like the way that they react, the way they form bonds with other elements. Okay, so those are the properties that we discuss, and those are similar for the isotopes. And also physical properties include like melting point, boiling point. All those are different. So, for example, for isotopes, I can give you an example of hydrogen. This is hydrogen 1 1. Then we have hydrogen element with one neutron, one proton. So that is called as deuterium. Okay, and then we also have tritium, which has 2 extra neutrons. So those are isotopes of hydrogen. Like that, other elements do also have isotopes, and most of the isotopes, in some cases, they are kind of a radioactive. So basically, they undergo decay process. Okay. Now, what keeps a nucleus stable? Now, this is very important part. Now, this question, we need to understand the forces inside a nucleus. So any two protons will repel each other strongly inside a nucleus due to electromagnetic forces. So we know that protons are positively charged, so they will repel each other inside a nucleus. So there will be strong repulsion because nucleus is very tiny space. So we know that the electromagnetic forces depends on two factors. The force depends on the charges, that is, and it depends on the distance square. So the smaller the distance, the stronger the force. So there is very strong electromagnetic force between the protons. So why they remain stable inside a nucleus? Because there exists another force, that is strong nuclear force. Okay, inside a nucleus. Now, strong nuclear force is attractive in nature. So it basically acts like a balancing force toward the electromagnetic repulsion force, and it acts between nucleons. So it doesn't have to be between protons and neutrons. It acts between protons. It acts between proton neutrons, and acts between neutrons and protons as well. So any nucleon inside a nucleus, strong nuclear force is highly active. Okay, it is extremely short range. It is not. So that's the reason why it can't exist outside a nucleus, because its range is only 10 raised to minus 15. That is probably the size of the nucleus. So that's why we only see this effect of forces when a nucleus breaks or a nucleus is formed. Okay, or some effects of nucleus, and then it is the strongest force of the universe. So basically, in that particular range, 10 raised to minus 15, strong nuclear force is highly dominant, and that balances the electromagnetic repulsive force, which keeps a nucleus stable inside a nucleus. Okay. Now, when we talk about other different elements, if I plot a graph of number of protons versus number of neutrons inside a graph, inside a nucleus, then you will see that the expected was the number of protons and number of neutrons should be same. But in reality, what happened is like the number of neutrons is greater than the number of protons for heavier nuclei like uranium or some other elements. But for lighter nuclei like carbon, nitrogen, the number of protons and number of neutrons is same. So what will be the reason? They ask this question. What will be the reason why there are more neutrons compared to proton for a heavy nuclei? So the reason for this is the size. As the size of the nucleus increases, what happens? The strong nuclear force starts getting weaker because it is extremely short range. So because of its shorter range, what happens is like as the size of the nucleus increases, it starts getting a little bit out of its range. So the strong nuclear force starts falling weaker for those newly added protons and neutrons. Okay, while the electromagnetic force keeps getting stronger because electromagnetic force has an infinite range. Okay, so because of this, the repulsive force increases and the attractive force is falling short. So what happens? This is why the more neutrons are added. While the neutrons increases the strength of strong nuclear force without increasing the repulsive force, because neutrons are neutral in charges. So we know that it won't add any electromagnetic force, but it will definitely add strong nuclear force. So that's the reason why there are more protons, more neutrons compared to protons inside a nucleus. Why? Because strong nuclear force is a short range, and as the nucleus size increases, it starts falling weaker outside that range. Okay, is this clear to everyone? Okay. Now, whenever there is an imbalances inside a nucleus, so those two forces are continuously balancing each other out. But in some cases, what happens is like a nucleus becomes too heavy for strong nuclear force, the size becomes too big, or sometimes there is some kind of imbalances between the forces. Now that will lead a nuclei to be unstable, and whenever there is an unstable nuclear, the possibility that it will undergo a decay process. Okay, a decay process happens to achieve a stability. So an unstable nucleus decays through multiple paths and can reach a stable nucleus, and that's the decay process that happens in nature. Okay, but the decay process is two important words that we need to remember, that is random and spontaneous. Why it is random? Because we can't predict when it will happen. And why it is spontaneous? Because we can't influence or modify the process. So for example, you do anything, but if the nuclei is supposed to decay after 1 year, it will still decay after 1 year. Okay, so it is so random that we can't predict and we can't influence it. And we know that if it is decaying, can we make it decay faster? Can we make it decay slower? Or can we change whether it is going from alpha decay to beta decay? We can change its path. We can't modify that process. That's the spontaneity, because we can't influence by any other external means. So whatever actions you take, you can't change its decay constants, you can't change its half-life or everything. That is basically the random and spontaneous about the decay process that we need to know. Okay. Now, what are different types of decays that we know? We know alpha decay, beta decay, and gamma decay. So, if we quickly talk about the alpha decay, if there is an element which is of A and Z, means this is a parent nuclei that we talk about. Now, whenever an alpha particle is released, what will happen? Two protons and two neutrons in a form of an alpha particle, it is released. So that's the reason why the nucleon number will reduce by 4, because it is a proton plus neutron. So two protons and two neutrons are going, so 4 will be subtracted, and then 2 will be subtracted from the proton number. That's for the daughter nuclei. So alpha particle is 2 protons and 2 neutrons. It is a helium nucleus, and it has a charge of positive E. It does not have any electron. It is just a helium nucleus. Okay, that is the alpha decay for you. Then beta decay. There are two beta decays. There is a beta minus decay first. We will talk about in beta minus decay. There is the nucleon number does not change, and a proton number is decreased because there is simultaneously electron is released. Just 1 second. Proton number is electron number is the -1 for the, and then there is another particle that we will talk about, that is antineutrino. Okay, so the beta minus particle is electron. Okay, it is a beta minus particle. Now we also need to understand what happens in this process actually. In this process, a neutron converts into a proton. So inside a nucleus is as it is. Okay, nucleus is not changing. It is the only change inside a nucleus. What is happening is a neutron is converting into a proton. Now, if you look at this reaction, on the left hand side of the reaction, there is a neutron, and neutron is neutrally charged, correct? So it is 0 charge to the left hand side. So on the right hand side, there has to be balance of charges. So a proton is released. Proton carries a positive 1 charge. So simultaneously, an electron is also released, because electron will have a negative charge. The positive negative will cancel out, and that's the reason why an electron is simultaneously released. Now, electron and this new particle, that is antineutrino, will be released outside the nucleus. Okay, so if there is a nucleus like this, so electron and a neutrino, antineutrino, will be released, and this will turn from X to Y. Okay, so this is how the beta decay happens. Now, important thing here is that's the reason why a proton is, wait a second, I have made a mistake here. I think so it has to be Z plus 1. Yes, because proton is added. Okay, now when we add this, then you can see the balance is happening, because Z plus 1 minus 1, you can see the nucleon numbers and the proton numbers are balanced on both the side of the equation, and that's how every equation, every nuclear reaction has to be. Okay, that is a beta minus decay for you. Okay. So antineutrino was not discovered during beta decay. Later on, it was hypothesized that first the energy of the electron, that the energy of an electron must be constant. Everybody predicted that the energy of the electron must be constant. But we found out that in every beta decay, the energy of the electron is different only. So there is a range of energy of electrons. So somebody hypothesized that where the extra energy is going, because if there is a fixed nuclei converting into another fixed nuclei, we know everything about both those nuclei. The amount of energy that needs to be released has to be carried by the electron if that is the only particle that is releasing. But there was a discrepancy in the conservation of energy. So somebody like the person was Fermi who thought that there must be another particle who we are not able to detect right now, but there must be some other particle that can carry that energy, and we made that theory that there must be a particle. Okay, later on it was discovered that it was an anti-neutrino, which is very hard to see because it is very less massive, like it is almost massless, and it hardly interacts with anything, but it is released during a beta decay. So anti-neutrino was discovered at that time, which carries the extra energy. So basically the energy in the beta decay is shared between electron and anti-neutrino. That's the reason why the sharing is random. So sometimes anti-neutrino carry extra energy, electrons can carry different less energy. Sometimes electron carry more energy, antineutrino carry less energy. So they can share the energy. That's the reason why the electron had different range of energies. Okay, and that was also the base or the for the hypothesis that why there is a discrepancy in conservation of energy. So we proposed a particle and we discovered it later on. Okay, so later on in beta plus decay, also a similar kind of a particle is released, but this time what is happening, there is a Z+1 happening because there is a positron that is released. Now positron is another particle that was discovered during this process, and then there is a neutrino. Now difference between a neutrino, antineutrino, or electron or positron is one important thing. First you need to understand that every particle has an antiparticle. Okay, so there is a proton, there is an antiproton. If there is a neutron, there is an antineutron. There is an electron, so there is not anti-electron, but anti-electron is called as positron, which is a positive version of electron. It has same mass, same behavior, but it is a positive in charge. Okay, similarly there is a neutrino, there is an anti-neutrino. Okay, now if you keep asking why exactly this happened, why anti-neutrino is released, why not neutrino is released, all those questions require some deeper knowledge of particle physics, which we are not covering at this level. Okay, it was there in previous syllabus, but it is removed, I think so, in new syllabus. Mhm. Yes, yes, it becomes -1 year. Okay, so that is correct. Okay, so this is what the beta plus reaction looks like. There is a positron that is released, and positron is a beta plus particle. Okay, you only have to remember those few particles, and their behavior is exactly same. Electron and positron only differ in charges. Everything else is same. Mass is same. In the beta plus decay, what is happening? There a proton is converting into neutron. Okay, so proton has a positive charge, neutron has zero charge, neutron has a zero charge. So positron has to be released so that the charges on the both side of the equations are balanced. Okay, so this is a beta decay for you. Now the question asks, what is a and a comment on the energy of the beta electron during the beta decay. So we need to understand that energy released in beta decay is distributed unevenly and randomly between electron and antineutrino. Okay, thus the electron where energy varies between a range because of conservation of energy. So this is very important statement. Okay, because electron can have a max energy, it can have minimum energy, but it always comes in a range because the sharing is uneven and random. Okay, so this is an actual question that comes in a question paper. So remember this important part. And then there is a gamma decay. In gamma decay, what happens? There is a excited nucleus. Excited nucleus, I mean to say, it has some extra energy to release, and then there is a stable state of a nucleus. Okay, so to achieve a stable state, it releases energy in form of a photon. Okay, so a nucleus can also have a higher energy and lower energy. Was not discovered until beta decay was discovered. Okay, and this was very surprising discovery because this photon that is released is a gamma range of photon wavelength turns out to be roughly around 10 raised to -15. Okay, which is extremely like shortest wavelength. Okay, now the shortest wavelength, if we are able to detect that, this tells you about information about a nucleus. Okay, so those nucleus whenever they give you gamma decay, we have gamma microscope, gamma ray microscopes, which can tell us information about the nucleus of an atom. So even if it is, you can't see an atom or a nucleus of an atom, the gamma decay or the gamma photon that are released can be visible or detected by some machinery, and that tells us information about the nucleus, where are they, and all the positions about them. Okay, but important thing here is the gamma decay provided us the evidence, the very important evidence or the existence of the discrete nuclear energy levels. Now, what does that mean? Discrete nuclear energy level tells us that, like electrons in an atom have different orbitals, okay, representing different energies. Okay. Similar way, inside a nucleus, neutrons, protons can have different energy levels, and they are discrete. It means they can't have any random energy, but some fixed energies are assigned to them, and they can move and make transition between one energy to another, and between energy levels inside a nucleus while releasing a gamma photon. So a nucleus, even if it is stationary, uh, the protons and neutrons can have a higher or lower energy as per the energy levels, and that was the major discovery that we had in gamma decay, of nuclear energy levels. Okay, then we can learn some properties of alpha, beta, and gamma decay. So if I talk about the mass of alpha particle, it is roughly around 10 raised to 20 minus 27 kg. Okay, while the beta particle comes under 10 raised to minus 31. So it is basically 10,000 more massive. Alpha particle is 10,000 more massive than the beta particle. So the mass itself tells us which path the nucleus will take. So try to understand. A nucleus in the initial state depends on how much energy it has, decides whether to go by alpha decay, whether to go by beta decay, or whether to go by gamma decay. Because energy released in alpha particle is very large, because alpha particle has a lot of mass. So then beta particles, which have lesser mass than the alpha particle, and then the gamma particle, which is almost massless. It is massless basically. So yes, gamma decay, what happens? A nucleus which is in excited state, when protons and neutrons carry some extra energy, they release that energy in a form of a photon. Okay, and that photon is usually of a gamma range, like 10 raised to minus 14, 15. That is the shortest wavelength that we can detect. Okay, so protons and neutrons inside a nucleus itself can carry extra energies, and those energies are discrete, because we have seen in the even when there are two electrons which have higher or lower energy, they can make a transition upwards, and we get an emission and absorption spectrum. Like that, we can get a spectrum, but of the nucleus. Okay, telling us about the nucleus, not of the electron, but of the nucleus. Inside the nucleus, what story is happening. We can get that information from the gamma photons if we detect them. Okay, so this provides us evidence that inside the nucleus also there are multiple energy levels. Okay, is that clear? So the neutrino has almost like very less mass, 10 raised to minus 34, and the gamma particle, that is a photon, it is electromagnetic wave. It is almost mass. It is massless, and we can see that each particle carries like tens and thousands of times of uh, mass. So the higher the mass, the more energy it requires to release them. Okay, remember that. And also the charge. If you look at the alpha particle, the charge is positive 2e. Beta minus particle, that is electron, is minus e. Positron will have plus e, and gamma has zero charge. Okay, that is very. Hmm? That is a neutrino. So remember the sign for the neutrino. It is like a V, but it is like curled V. Okay. So a neutrino dash agar likhenge, so that is anti-neutrino, and if you don't write a dash, that is a neutrino. Both have same masses, but one is particle, one is anti-particle. Okay. Then there is a electric field. What is the effect of electric field? So imagine there is a positive and negative plate. Now what will happen? A beta particle will accelerate upward to the positive plate, while the alpha particle, being positive, will attract to the negative plate, and the gamma particles goes undeviated. Correct? Now this is very simple, but the more important question here is, what will be the radius of the curvature? And we can see that the radius of the curvature of beta particle is greater than the radius of the alpha particle. And why is that? Because beta particle will experience higher acceleration compared to the alpha particle. Barabar? Why? Because alpha particle is more massive. So more massive, you require more force, so less acceleration. Try to understand this. More, if you have force, but the object is more massive, so it will accelerate less. That's the inertia, law of inertia. Similarly, if there is less massive particle and if you apply same force, it will accelerate higher. Correct? So since both of them are in the same electric field, the beta particle has a higher curvature while deviation while compared to the alpha particle. Okay. So those are the few important things that we need to know. And in the magnetic field, again magnetic force also, you can see the curvature of beta particle is higher than the curvature of the alpha particle. The direction of the magnetic force will be predicted by Fleming's left hand rule. Okay. So the middle finger in Fleming's left hand rule represents direction of the current or a positive charge. So alpha particle, if you align the field is going into the phase, the thumb will point upwards. So that's why the alpha particle will take a deviation upward. While the beta particle, being negatively charged, it will take deviation downward. Gamma particle is undeviated again because it is neutral in charge. Okay. And we need to remember that the radius of the curvature can be measured by this equation, R is equal to mv by qb. Okay. In the magnetic field chapter, we covered this. Two important other properties that we need to know about alpha and gamma particle is the penetration depth. See, alpha particle being more massive, it can't penetrate piece of paper also. It can be stopped by even piece of paper or similar kind of object. Beta particle can penetrate through this piece of paper, but it can be blocked by some sheet of metal. It can be aluminum, copper, or anything. Okay, but it has to be a little bit a thin sheet can block the beta particle. And for gamma particle, it can penetrate through everything. Okay, except if you have very strong block or very thick block of lead, the lead will stop that penetration to some level. But still, there will be some probability that a gamma particle can win through. Okay, but these are the abilities. So gamma particle has the highest penetration depth, alpha particle has the least one. Similarly, another property if we talk about is the ionization power. Alpha particle will have highest ionization. What is ionization, guys? Ionization is a ability to knock out an electron from an atom. Okay. So alpha particle has that highest ability. So whenever alpha particle is released, it interacts with the nearby air or a medium and it ionizes it and loses its energy basically. That's why it can't go further in air. Alpha particles can't travel very far because they ionizes the nearby air molecules. While the gamma particle is least ionizing, okay, so it won't ionize the air. Okay, beta particle comes in between for the ionization section. Okay, is this clear so far, guys? Then we will talk about some radioactivity and laws of radioactivity. So first, when we talk about law of radioactivity, we need to know this statement. At any given time, the negative rate of decay of radioactive nuclei is directly proportional to number of undecayed nuclei at that time. Number of undecayed nuclei at that time means if I start with some number of nuclei and if I wait for some time, okay, the rate at which the decay is happening is directly proportional to how many nuclei are remaining which have not decayed yet. Okay, so this is the statement that we need to remember. Okay, usually when we trace number of undecayed nuclei with respect to time, we get an exponential curve. Okay, so if you observe this curve carefully, there is an n naught, that is initial number, and this graph goes asymptote to the x-axis. Okay, so if n naught is the initial number of nuclei, okay, we will introduce one more term that is called a half-life. What is half-life? Half-life is the time taken by a radioactive nuclei or a sample to decay up to its 50% of its initial value. Okay, so 50% of its initial value. So for example, here if you can see from n naught to n naught by 2, okay, it will decay up in one time period. So time, this is half-life. T one half is the half-life, that is. So in one half-life, it will go from n to n naught by 2. Okay. Similarly, in another half-life, what will happen? It will go from n naught by 2 to n naught by 4. Okay. Similarly, it will go n naught by 4 to n naught by 8. So like this, every decay, what will happen? It will keep on decreasing. Okay, by half. Okay. And what I have not drawn here is the, let's say, the new nuclei. It decays into a new nuclei. Correct. So whenever a decayed nuclei are there, the number of decayed nuclei has to pass through this 50%, because at 50% these are the decayed nuclei. Okay, this is the number of decayed nuclei. It increases like a upward exponential. Okay, another thing that we will talk about is that if there are n number of half-lives that happens, then the number of the undecayed nuclei goes from, like, you can divide it by 2 raised to n. Okay, so each half-life it will be dividing by 2, so n number of half-life it will be n naught divided by 2 raised to n. Okay, and number of decayed nuclei can be found by, so this is number of undecayed nuclei, don't get confused with the decayed and undecayed one. Okay, and that will be n naught minus n naught by 2 raised to n. Okay, so this is very simple, but very they can ask multiple questions based on this. Okay, so they give you some random time, but if you measure, if you have the half-life, you will measure that time and you will get that, okay, this time is equivalent to 3 half-life. So it means the initial number will reduce to n naught upon 2 raised to 3. So that will be n naught by 8. So that will be in 3 half-life, it will be 1 by 8 of the initial value. Like that you can answer the question. Okay, then we have devices like Gregor counter. Okay, now Gregor counter is what we use to measure like how many decays are happening per unit time. Okay, so it detects the particle when you place it near a radioactive sample. It can't decay gamma radiation, but it do decays other radiation like alpha and beta. The intensity of the count rate, and a count rate is number of particles detected per unit time, depends on what distance there is between the sample and the Gregor tube. Okay, so we have a sample that keeps on decaying, and then we have a Gregor tube, which usually whenever a particle is detected, it counts that particle, and we get a count rate based on it. Okay, we also need to know another quantity that is called background radiation. It is basically the residual radiation that is there everywhere right now. Also, a lot of radiation is passing through your body. Okay, so that is present all the time. The sources are basically the cosmic ray for the sun, the rocks, the concrete, okay, the roads, okay, and the past nuclear bombing, everything. There are multiple sources of background radiation, but those usually interfere with the Gregor tube, because Gregor tube also can't differentiate between the particles coming from the sample or from the nearby background radiation. So a Gregor counter always detects the background radiation, which causes the count rate to show a zero error. So usually when you see a graph having a count rate, you will get a extra, like the graph will go flat, not to zero, but some line above. So that is background radiation. Okay. So what we usually do is we basically subtract the background radiation from each reading. That's how we deal with the zero error of the background radiation. Okay. Then we have another term like it's called activity. Activity is nothing but it is a rate of radioactive decay. Okay. Or so activity also, like a given sample also decreases in a form of an exponential curve. So when the rate of decay, what happens? The rate of decay also decreases with the time. So similarly, activity also decreases with the time. So that is something that we need to know. The unit for it is becquerel or second raised to -1. Okay, those are the unit of activity. Now those terms are related, but now when we will talk about the math of radioactivity, now this is the HL part. In HL part, you will find that the law of radioactive decay, at any given time, the number of undecayed nuclei, that is n naught, is directly proportional to negative rate of decay. So that is a derivative function with respect to time of dn by dt. So that is rate of decay. Okay, number n is what? Number of undecayed nuclei. So if we convert this to this, thus you can get a constant. So we relate those directly proportional. So lambda is nothing but it is a constant of proportionality. Okay, which we call as decay constant. So it is a constant of proportionality. And if we solve this differential equation, dn by dt is equal to minus lambda into n, we will get a solution like n is equal to n naught e raised to minus lambda into t, which gives us number of undecayed nuclei at any given time. This equation is given in data booklet as well. So do expect problems to be asked on this equation, where n naught is the initial number of the nuclei. Okay. Now, if I just rearrange this equation, I will get another equation, dn by n is equal to minus lambda into dt, which gives us the probability of decay of one nucleus. What is the probability? What are the chances that one nucleus will decay? That is given by dn by n. Okay. Similarly, if I just rearrange this again, I will get dn by n upon dt. So which is defined as probability of a decay of one nucleus per unit time. So that is the definition of decay constant. Okay. So if they ask you what is the definition of decay constant, just say probability of decay of one nucleus per unit time. Okay, that is a decay constant definition. Okay, we can relate the time half-life with the decay constant by this equation ln by 2. This is also given in data booklet. So what is the half-life? Half-life is when the initial quantity goes to half, so n by 2. So if you substitute that in this formula that we got earlier, so time will be replaced by t half and the n will be replaced by half of n. So that will give us this equation, and if we just solve this, n naught will get cancelled out, and solving this will be taking log on both sides, we will get something like this. Okay, the half-life is equal to ln of 2 by lambda. Ln of 2 is basically natural log of 2, which is equivalent to 0.693. So this is the formula that we get for n is equal to n naught e raised to minus lambda into t. Okay, n naught is the initial number of particles of the nuclei. N is the number of nuclei that have not decayed at given time t. Okay, so at a particular time t, if you choose how many nuclei are remaining, that will be taken by this equation where lambda is constant. Now, once you get this, now what is the definition of half-life? That half-life is the time until which the quantity, initial quantity, will be reduced to half. So if I substitute t is equal to t half, that is half-life, then the initial quantity will be reduced to n naught by 2. Okay, so that's why in the same equation I will replace the n by n naught by 2, that is the, it has become half in the, and I have replaced the time by half-life. Okay, that is capital T. So if you solve this equation, n naught by 2 will get cancelled, so only 1 by 2 on the left hand side will remain, and then we take the log, natural log, then move little bit terms, you will get that the half-life will be equal to natural log of 2 upon lambda. Okay, you don't need to remember the derivation, but this equation is there. They will probably ask if they have given you decay constant, then they have probably also given you the half-life. You can relate both, and unit of decay constant is second raised to minus 1, because you can see the time period is on the left hand side, so time period will measure in seconds. So this is not wavelength. Most of the students get confused with the lambda as a wavelength, but this is in this chapter related to decay. It is decay constant rather than wavelength. Okay. Now the one more, as I mentioned earlier, activity is rate of decay. Activity is rate of decay. So here, at any given point of time, activity is directly proportional to the number of undecayed nuclei. That is something that we know, because activity is nothing but rate of decay, and we know that from the law of radioactivity, the rate of decay is directly proportional to number of undecayed nuclei. So this is the same statement that I'm saying. Okay, just 1 second. Yes. Now we also get few equations based on this. So activity is nothing but negative rate of decay. You can see minus dn by dt. Okay. Now see this in this previous equations, wherever I have written dn by dt, you can replace that with a. Okay, with the negative sign going out. So I will get this equation first. So a is equal to lambda into n. What is a? A is the activity. A means a negative rate of decay. Okay, it is a negative rate of decay. So if a is equal to lambda by n, if I plot a versus n graph, I will get a graph, straight line graph with a slope of lambda. Because you can compare this with y is equal to mx, where m is a slope. So this is, we will be, so a versus n graph, remember that the slope will be lambda and it is straight line passing through the origin. Okay. Now earlier we know that n can be replaced by this formula. What is the formula for n we got? N is n naught e raised to minus lambda by lambda times t. So we can replace this and we will get something like this. Okay. Now if I replace the lambda into n naught by this, then you will get this equation. Now all those equations are related. I know maths part is, you will always see multiple equations being boxed out, but remember this, all those are given in data booklet, and when we do problems based on this, these formulas will get more clearer, but they are all related. Okay. Even the count rate is having the same. So activity, if a naught is initial activity, then we get a equation which is similar to n, which is a naught into e raised to minus t, and even we replace a with a count rate, even the count rate will have same exponential curve, which is given by same similar kind of a equation. Okay, so all those equations have very similar form because all of them follows exponential decay, and then the equations are carried into questions. Okay, is this clear so far? I know when we do questions based on this, it will be more clearer, but for right now, it is just what the law of radioactivity suggested in the beginning. That is the law we are building mathematically, and some mathematics have given us some equations. Okay, where decay constant, you have to remember the relationship for the n and not an n e raised to lambda by t. This is something that we need to remember, and the activity and the number of undecayed nuclei relation we need to remember. Okay. The last part of this chapter, it talks about energetics of the nucleus. So what happens with the energy of the nucleus? Okay. So when we talk about energy, there is some description of mass as well. So now we will talk in terms of atomic mass units. What is the atomic mass unit? It is a unit of mass, and it is equivalent to 1/12 of mass of carbon 12. Okay. So basically, all the protons and neutrons have so less, like they are so less massive that we can't use 10 to minus 27, minus 31 all the time. So we replace them by U. This conversion is given in data booklet. Okay. Then we also need to know mass energy equivalence at nuclear scale. There is one important thing that you need to remember at nuclear scale: mass and energy are equivalent. So what happens at nuclear scale is that there is a spontaneous change between mass and energy. A mass can convert into energy, and energy can be converted into mass. Okay, try to remember this. Okay, it is not necessary. There is a mass energy equivalence, and this is where the Einstein's E is equal to mc square equation comes into play. Okay, the mass and energy are related by this relationship. This is at nuclear scale, they are related and they can convert into one thing, one or other thing. Okay. Then we will talk about the more important part, that is mass defect. What is a mass defect? There is a difference in mass of individual nucleons. Okay. So a mass of a nucleus and the mass of the individual nucleons, they are different. Okay. So for example, just think of, if I have two protons and two neutrons, and if I add the masses of two protons and two neutrons, now that will be higher compared to the mass of helium nucleus, which is also made up of two protons and two neutrons. So where the extra mass has gone? Okay, again I will say, if I have two protons and two neutrons separated, not inside a nucleus, separated, individual, their masses, when I add, it will have a higher number compared to the mass of a nucleus where two protons and two neutrons are confined inside a nucleus. So there is a difference in that masses. So that is called as mass defect. Okay, and that mass defect is because of the energy, mass energy equivalence that we talked about. When a nucleus is formed, some mass is converted into energy. Okay, so when you have two protons, two neutrons, they are separated and their mass is higher. But when you put inside a nucleus, some of the mass is converted into energy to form that nucleus. Okay, so that should be that thing we need to remember. Okay, now how do we calculate mass defect? So for example, if I have a nucleus AZ, okay, then I need to have a number of neutrons, so that's why I will do A minus Z into mass of a neutron and add the mass of proton. Now these are the masses of individual protons and neutrons outside the nucleus, and then we have the mass of the nucleus itself. And when we subtract those, we will get the mass defect. Okay. Now why do we calculate mass defect? Mass defects leads to tell us exactly how much energy is required to form a nucleus. So that is called as binding energy. Energy required to form a nucleus from individual nucleons. So if you have separate protons and neutrons, how much energy will be taking to bring them together inside a nucleus? That is a binding energy, and that can be calculated using mass defect. Okay, it is also the energy, same amount of energy that is released when the nucleus is broken down into individual nucleons, and it is the energy equivalent of the mass defect. So mass defect, see, understand this: a proton will outside a nucleus will have a higher mass, and proton inside a nucleus will have a less mass. That's the mass defect. Okay, so inside nucleus, हम लोग जो mass देखते हैं, what we see is that the mass of the nucleus is less compared to the mass of individual protons and neutrons if we add all those. Okay, in real world it does not happen, but inside a nucleus it happens because some of the energy has gone into forming the nucleus. Okay, so mass is converted to energy. That's the Einstein E is equal to mc square. Okay, is that clear? So binding energy is that kind of energy, that is the mass converting to energy. Yes. Yes, that is one formula, because usually they will give you masses of the mass of proton and mass of neutron is given in data booklet. Okay, they will give you mass of nucleus, and they will give you the proton and neutron number, and we can subtract that. We get this formula. That's the only way we can calculate this. Okay. Now binding energy has three ways to how to calculate binding energy. So first thing, let's calculate. The first step is always calculate the mass defect. Now if the masses are given in kg, then the binding energy can be found by multiplying by c square, that is speed of light square. Okay, and this will give you binding energy in terms of joules. Now this is not the ideal way to do it, because most of the time the masses are not given in kg, they are given in atomic mass units. So this is just one way to tell you if the binding energy they are asking in joules, you can do this if the masses are given in kg. But as I mentioned, the most used one is masses are given in atomic mass unit. So you take the mass defect and you multiply with 931.5 mega electron volts. Okay, that is just a conversion factor basically. Instead of doing c square and getting in joules, you are getting in electron volts. Okay, so 1 electron volt is also units of energy, and mega is 10 raised to 6. Okay, so that is just a conversion factor, and you need to remember this as a formula. This is not given in data booklet. Okay, so I will suggest you to remember this. Binding energy can be found by taking the mass difference, okay, between the individual nucleons and the mass of the nucleus itself, and then multiplying it with the 931.5 mega electron volts. Okay, that conversion factor is not given in data booklet, so you need to remember that. Okay, this will give you binding energy in terms of mega electron volts, and you will find that most of the questions ask binding energy in terms of mega electron volts only. Okay, and you need to know the conversion between how to convert a mega electron volts to joule and joules to mega electron volt. That kind of conversion needs to be known. Okay, that is given in data booklet. There is another way. Sometimes they give you binding energy per nucleon. Per nucleon means what? Whatever the binding energy is, that is divided by the nucleon number. Nucleon number is basically mass number. Okay. So, for example, there is a 235 number of for a uranium, and uranium binding energy per nucleon is given as 7.6 mega electron volts. Now, if I want to find the binding energy of uranium itself, I need to multiply with the nucleon number. Okay, so most of the you will also find in some question binding energy per nucleon is given. So to get the binding energy, you need to multiply with the number of nucleon to get it. Okay, so this is also another way to get binding energy. So these are the three ways they can probably ask, and we can we see how we can get a binding energy. Okay. Now some questions also ask how we can calculate the energy released in a reaction. So for example, if there is a nuclear reaction that is happening, there is always a reactant side and there is always a product side. Correct? So if you know the reaction, we need to understand that how do we calculate energy release in reaction? You have to take the sum of masses of the reactants in U, means atomic mass unit. Don't do it in kg, convert that in atomic mass unit first and then add all the reactants masses. And then we subtract all the products masses. Whatever the particles nuclei are present in the product, we'll add those masses and then we will subtract them. Okay, that will give us the mass defect. What is the mass difference between the product reactants and products? Okay, because mass of the reactants will be higher compared to the products, because mass will be converted to energy, and that energy will be released in a reaction. So we take the difference in masses, sum of masses of reactants and products, and we multiply that with again the conversion factor to the energy 931.5 mega electron volts. Okay, this is the formula that you need to remember for the energy released. Okay, if the reactants and products, instead of giving you the masses of reactants and products, if they have given you the binding energy of reactants and products, we have to subtract the binding energy of products minus reactants. Ulta karne ka. Earlier we subtracted the masses of reactants and products, but the binding energy will be higher for the products compared to the reactants. Okay, this is when we get the energy released. Clear? So remember that whenever there is a binding energy that is higher for the products compared to reactants, energy will be released. Okay. So, and we also don't include the binding energy of individual protons and neutrons, because individual protons and neutrons are not bounded to the nucleus yet. Okay, so we won't take their energy in those equations because they won't carry that energy. Okay, so we need to note this. The last part of this is binding energy curve, which looks like this. So this is binding energy per nucleon graph, and you need to remember the shape of this graph, guys. They ask you multiple questions based on this, but you need to remember the shape of the graph. Okay, now what you need to also remember, at this point there is a peak, and that peak is given by that is a peak for nickel. Okay, so nickel, iron, cobalt, those are the elements that has higher binding energy curve. Okay, any elements above this will undergo fission. Okay, we will do fission and fusion, but then other elements will go fusion. Okay, and both during fission and fusion, both energy is released, because whenever you make a fusion or fission happen, you always move closer to this peak. So higher binding energy for the products will be there in both the cases. So since there is higher energy of the products, as I mentioned, energy released is binding energy of product minus binding energy of reactants. That's why there is a positive energy release. Okay. So this is all it is there in this entire chapter. Okay. Uh, I think we have covered everything in detail. All the questions that they can probably ask is covered. Okay. Only thing that we need to do is practice for this chapter.